this computer. All right, so we're, oh, damn, it's 13, so, but that's all right. Okay, so we're gonna do a short introduction, review of code systems, and do Hamming codes. And in particular, we're going to do the famous Hamming 7.4 code, which was the example in Shannon's 1948 paper, because Hamming was a colleague of Shannon. All right, we've talked about all of the abstract. It's the same every time. So we're now on chapter 13. This is the crazy mix of stuff we're looking at. Okay, last week I did a pretty quick review of the material we covered so far and a rough idea of where I want to take us. This week we're going to finish up the Hamming error correcting codes, in particular the famous 7.4 code, which Shannon used in his 1948 paper. Hamming had, Shannon had shown an existence proof for error codes, but not a constructive proof.
Excuse me, Bob.
Yeah.
Are we supposed to be, is the screen supposed to have your text on it? Because I'm seeing you on the screen and the text very tiny up in the right.
No.
I see it correctly. So her view must be incorrect. She must.
Yeah, you got to go up in your upper right-hand corner and click something. I don't quite remember.
All right, I'll fool around with it. Sorry about that.
Yeah, it's good for everybody else, so.
All right.
Okay. So Shannon, in his original paper, had done a existence proof. This proves that something is true, but it doesn't tell you how to do the answer. He did show that one particular code, the Hamming 7.4 code, was an example of how it would work. And so in addition to proving that it could be so, there was at least one code at the time that existed that worked. And we're going to deal with that one in pretty much detail this week. Okay, last week, or a couple of weeks ago, I guess, we had done Huffman compressing codes. So we discussed the average cost per bit, which is what's minimized in the Huffman codes. The instantaneous codes, they're a variable bit code length, but they're an instantaneous code or prefix prefix type of code, because a special symbol always tells you when you're starting a new code. And it is a variable length code, as I just said. Okay, so if you've got an alphabet and we've got a finite subset of that alphabet, all combinations of alphabets, is prefix free whenever there's a special symbol W in the subset that is the initial sequence of every code word. So, and we say that those are prefix free, and it is injective so that it will allow decoding. So it is a we receive a sequence of bits. Then every time we find the special symbol A1, the code of it was the first message had an A1. We look, then decode it according to the rules and look for the next version of a code that has an A1. So that's why they're called, prefix codes are called instantaneous codes or self-punctuating codes. A prefix-free code system distinguished because of its prefix property. That's the specific item that tells you that there is a start of a new code. So if we consider a code with code words 9 and 55, this has a prefix property. However, if we had a code 9, 5, 59, and 55, it does not, it's not a prefix code, not a prefix-free code, because 5 is a member of 59 and 55. So you'd either be using 9, in which case the other 3 wouldn't work, or 5, in which case the 9 wouldn't work. Okay, somebody is still got their stuff on and they're getting a phone call. Okay, so as an example, suppose we had 0, 1, 2, 3 and B0, 1, then we can map every element of A into B star using 2 different ways. One of them, C, is 0 goes to 0, 1 goes to 1, 0, 2 goes to 1, 1, 0, and C3 goes to 1, 1, 1. By reversing the same digits, C tilde, we can also completely map A into B star, but C is prefix free and C tilde is not. So in the previous list, if we had this set of bits, we can find that the 1 will find 1, 1, 1. So that will find the first one of 4. Then the next one has a 1. So we can do 1, 1, 0. So that's a 3. Then we do a 0, and that is a unique code. So we can recognize either a 0 or a 1. And it's a 0, there's a unique item, so you don't have to do anything about it. And that gives the 0 result. So we have 3, 2, 0. And lastly, you get the 1, 1, 0, which is 2 again. So we reconstructed the code 3202. Okay, if you were to use C tilde and reversed the order of these, there would be a number of zeros. Let me go up here. So 1 is not unique. So you could use a subset the 0, 1, and 2 with 0 as a prefix. And that would work fine. But once you got to 1 as the first code, the 111 wouldn't tell you whether it was part of either 1 or 2, or it was the 3. That's why C tilde is not prefix free. Okay. So the Morse code is a binary code, but it's not prefix free, which is why there's always a space symbol and with the space symbol, using a Morse code is prefix free, but it uses an extra symbol every time. Hamming codes. Okay. There are many, many ways of doing compression and correcting errors. And I analyzed the statistics. Let's see. All right. So there is a tremendous amount of ability for us still from Voyager, which is well beyond the solar system, into the Oort cloud, and we are still receiving the messages from Voyager. I can't remember exactly what the bit rate is. As I remember it, it's about 25 bits per second or something like that, that it sends the Voyager codes still to us. And part of the reason that it works so well is because, excuse me, the codes are well designed, and they have plenty of time to create bits between the symbols. Anyway, we started talking about human language, and we talked about how inefficient it is. We did a couple of different things. We did the zip probability distribution, which showed that if you do it by letters, E is far and away the most often letter, and Q is usually the last letter in the frequencies. And we did the whole description of the probability distributions for that. So if you take a look at the fact that average English words are 5 symbols, and the redundancy, turns out that the average word is less than 10 bits. So, however, if you use a 5 letters, then you need 25 bits, 5 times 5 letters times 5 bits per letter to express a message. 25 bits is the content of it is only about 10 bits. So it's pretty inefficient. But although it is very redundant, that's not a problem. Everyone uses many more symbols than the messages seem to require. And the reason is that the phonemes of the spoken language allows you to miss portions if you're in a party or something like that, and you'll be able to correct in your head the figure out what the appropriate word being spoken is. So I'm going to skip over this bit on how many words there are, and we've talked about this before, so I will just pass on. Okay, although there are many possible words in the language, as we said before, there's a very vast space of possible words, but the actual words are scattered very sparsely through this space. Many of the words like vorbi is not an English word, but it's a Romanian word and means to speak. So although we don't use many other languages do use some of the combinations that we don't use. So why don't we use fewer letters? Well, because it makes our communication by using all of this redundancy much less subject to errors. So if we had the list of 9,000 English 5-letter letters, then some of them are close together, others are quite far. So some might be 1 letter apart, like pride and prime, and we call those neighbors of each other. And how many typical neighbors does a word have? Well, we can consider all possible 5-letter words, and then each of the 5 letters could be changed by any of the 25 alternatives, and that would be 125, 5 times 25. Actually, only a few would be. So grove is on average 6 neighbors, not 25. Drove, glove, grave, grope, prove, and trove. So that's part of how we use the redundancy to see things better. There is a word game called doublets or word golf, and it was invented by Charles Dodgson. He's the pen name of Lewis Carroll and the author of Alice in Wonderland. And the game starts with 1 word and then stepping only with neighbors, using actual English words. You change it step by step into another word. It's called word golf because the idea is to reach the goal in the fewest number of steps. So can you turn head to tail in 5 steps? Well, oh, by the way, Rossmore News each week has a different name for the same word for the same game in the game section. I forget what they call it, but anyway. So we can have head goes to heel, goes to teal, goes to tell, goes to tall, gal, goes to tail. So again, there's only 6 neighbors here, and it is the fact that English is resistant to corruption by errors. Okay, let's skip the written version of this. We've talked about it before. Nevertheless, because English is so redundant, a few misword phonemes or stuff are usually no problem. The hearer corrects them automatically and unconsciously. Error correction wouldn't work as well if English words were more crowded together in that space of all possible words. Mistakes in one letter or sound would be more likely to turn the correct word into some other plausible word that way, and misunderstandings would abound. So although it is inefficient, it is a very real world error correction is important. Redundancy is not a bug, it's a feature. So in the previous lecture, we saw how Shannon's second fundamental theorem guaranteed that error correction is possible, provided that the communication channel allowed the information to get through. The amount of information conveyed by a channel is measured by its mutual information, using the Kullback distance. And the maximum mutual information for the channel is its capacity. This is the maximum rate at which the code's bits per second may go through the channel. If you're clever about inventing a code and our decoding procedure, we can send up to C bits per use of the channel while making the overall probability of error as small as we wish. As I said before, he provided an existence proof as opposed to a constructive proof, but we're going to talk at least about Hamming codes, which Hamming created a whole series of error correcting codes. So there have been many, many more types of error correcting codes.
Bob,
yeah?
just one quick question, kind of comment. What the previous slide, you basically can reduce the probability of error, but you can't totally eliminate it.
Oh no, yeah, that's correct.
So it's
Yeah.
it just says you can continue to reduce the probability, but it is potentially still there.
Oh yeah, yeah. Okay. So error correcting codes are based on the same idea we encountered when discussing the redundancy of English. You use longer code words, and the code words in our code will be scattered very sparsely in the set of all possible codes. So in some sense, and we have to define what that distance is, the code words have to be far apart. So there has to be a distance between code words. And that will make it easier to recognize and fix potential errors. Okay, so we start with the simplest possible error correcting code. We send 1-bit message to Bob, 0 or 1. There's some possibility that there's an error is made when the bit is transmitted. So Alice, in order to provide some redundancy, gives the same bit 3 times. And she either sent 0, 0, 0 or 1, 1, 1. So the way he can receive the bits, he could receive them incorrectly. He could get a 0, 1, 0 or a 1, 0, 1. So he simply checks if there are more zeros than ones or more ones than zeros, and decodes accordingly. So if there's more zeros than ones, then he says it's a 0, 0, 0. And if there's more ones, then he assumes it's a 1, 1, 1. And therefore he gets a 0 or a 1 bit of information. So does this actually help? It certainly does make more redundancy, but it also increases the opportunity for errors. What will this message actually improve Bob's chances of decoding Alice's message correctly? Well, let's suppose that they're in a symmetrical channel that we've talked about previously with an error E, and we'll call it to be 5%. So the probability of error if Alice sends her 1-bit message once without using any error correction is E 5% or 95%. And for the probability of getting it correct, and 5% of getting it incorrect. With his repeated 3 times, with Alice's repeated 3 times code, the likelihood that Bob receives all 3 bits correctly is 1 minus E to the 3rd, about 8.57%. So Bob will decode the message correctly if just one of the bits is wrong. There are 3 ways that that could happen. The first, second, or third bit could be wrong, and each one has probability 1 minus E squared times E, and 2 rights and 1 wrong, which gives us 0.95 squared times 0.05 or 0.045. So the probability that Bob receives the original 1-bit message is about 99% given this. So error correction does help. Instead of a 95% chance of a incorrect and asking to get it to resend, then you get a 99%, so that's considerably better. So Hamming distance, we can visualize how these codes work, and let's see, where can I put this so that it isn't in the way? Okay, so
Bob,
yeah.
before you get onto that, where do you come up with the 95% chance of transmission being correct?
That was an assumption. We're making an example. So the assumption was that any particular bit had a 95% chance of being properly transmitted.
I see. So that was just artificially inserted just to help see the math between the error correction versus the non-error correction type.
Right.
I guess what I'm trying to come to is there could be significantly more error depending on the amount of noise in the channel. So certainly you can, have situations where of the 3 transmissions, 2 out of the 3 could be incorrect, or 3 out of the 3 could be incorrect.
That would be a pretty bad channel, but yeah, it's potentially possible. But in the design, the engineering of channels, you usually try for something on the order of 0.99999% accuracy, not 0.95. Uh, so it's actually very much less likely than what the example showed in real life engineering. Even in the 1960s, when we had, pretty bad, we had about high-speed codes took 9,600 bits per second, as opposed to today, which are typically a billion bits per second and more. If you're going to be dealing with lots and lots of bits going through, you have to be very, very high probability of having the bits come through in the proper order, or you're just going to have to use a tremendous amount of error correcting, which slows things down. It's just in the real world, they're typically about 6 to 8 nines, 0.6 nines or 0.7 nines or 0.8 nines is typical for a channel coming through on, and for instance, an Ethernet cable. So potentially it's that way, but it's never been that much, even back in the 60s when we were using very slow channels, and a lot more noise was prone. That back then it was still about 0.9999. Does that help?
Yes.
Okay, great. All right, Hamming distance. So the 3-bit binary can be seen as the corners of a 3 of a cube. So 0, 0, 0 is here at the left corner, and 0, 0, 1 is to the right bottom corner, and you can go around for all the ones that there are. And the distance between any two of the possible 8 3 bits that could be sent, each is the one from 0, 0, 0, that's the starting point of the code, to the 1, 1, 1 is 3. That you can't go any, you have to go through any of the other corners. You always have to go between corners to get to a place. So if you went from 0, 0, 0 to 0, 1, 0 to 1, 1, 0 to 1, 1, 1, that would be 4. If you can find a shorter route, but you can never do less than 3. And so the 1, 1, 1, I'm sorry, the example shown here, the 1, 0, 0 to 0, 1, 1, that's the red, whoops, let's go back. All right, so from 0, 0, 0, you go to 0, 1, and then you go to 0, 1, 1. So the red ones there, these two corners, that's distance 2. In order to go to 0, 1, 0, 1, 1, where is that? That's up here. I'm sorry, that's starting up here. So starting from here, you go to here, go to here, go to here. So the red lines are the ones associated here. That's distance 3. And 0, 1, 0, that's the one in blue, to that has a distance of 2. But 0, 0, 0 to 1, 1, 1 has a distance of 3. So the information rate is the log of the number of bits 2 to the n in any code, log of that divided by n. So the information rate is never greater than 1. And the when they're exactly equal to 1 or m equals 2 to the n, then they agree and you get 1, or the best possible information rate, 100%. So how would our decoder work? We assume that all messages are equally likely and that errors are independent. Now, this is actually not very reasonable. In most systems, you get what are called burst errors. And burst errors are ones where if you have one error, you're likely the next bit is also likely to have an error, and the one after that. And the length of the bursts would give you information about it, but that would be basically you'd break all of the coding. So one of the things that you can do, and in practice it's not usually done, you could use the statistical property if you expect them to come, or you could permute the bits of the message. That is, the burst errors could be spread out. And then you decode in the burst form, in the permuted form, and then repermute the bits back to give the original messages. In practice, especially for instance in mobile phones, the property of the transmission channel are constantly changing. This is the Hedy-Lamarr idea of frequency hopping, and the constant swapping of transmission channels, instead of having a burst of errors for one user and destroying a whole lot of message, you swap it among several simultaneous users, and you divide the bursts among the users, bringing the number of burst errors much less than they would be otherwise. So we'll be always looking at codes that are 0 and 1 and some combination of them. And we're going to say that the size is m, and this is, you know, if n is, you know, 7 or something like that, 2 to the 3 would be m. So if m is large, then we can send a large number of possible messages. And as m increases, it becomes harder to distinguish between different messages when errors occur. So at one extreme, each error causes us if m equals 1, there's only one message, and therefore you don't have any problem. If you send anything, you're sending that symbol, and you can just automatically assume that it's in. But at the other extreme, if n was, 2 to the 10, 1024, then we can transmit lots of messages, but any error moves from one code word to another. So we can write the Hamming distance here as the sum of all of the bits in the X set of symbols and the Y set of symbols. So X and Y, so 0, 1 to the N is the number of possible messages. So it could be 0, 0, 0 to N, and every combination up to 1, 1, 1 of length N. And the distance between those is, you take all the individual bits of the N in the X and Y, and you find the absolute value of the difference between them, sum them, and that's called the Hamming distance. And as opposed to the Kullback distance, which isn't a metric, the Hamming distance is a metric, but it's a rather unusual one. We're used to dealing either with the Euclidean distance or with the Lorentz distance in special relativity, or the distance in general relativity. And this is a rather different one. So would somebody tell me what a metric is? Somebody choose your space bar and shout out.
Some quantified measure of distance.
Right. So a way in which you measure distance. So what particular type of metric is the Hamming distance? And since you can see that it's got the answer there, it's a version of the Manhattan metric, or sometimes called the taxi cab geometry. So if you're in a system such as streets, which you have to go along the streets, you can't go through the buildings, especially if you're in a taxi cab, then the red, yellow, and blue paths all have the shortest length of 12. So the distance in the Manhattan metric is not unique. And the Euclidean geometry, the green line, is the length of 6 square roots of 2, or about 8.5. And that is a unique shortest path. Okay, so more on Hamming codes. 2 code words, Alice uses 0, 0, 0 and 1, 1, 1. We're separated by a Hamming distance of 3. And that's a significant number. An error occurs in 1 bit. Bob receives something like 0, 0, 1, but with 1 bit error, the received 3 bits is still closer to the original 0, 0, 0. The Hamming distance 1, as opposed to the alternative 1, 1, 1, which has distance 2 from 0, 0, 1. Because the code words in 000 and 111 are separated by Hamming distance 3, a single bit error will still leave us closer to the original than anything else. So whatever Bob receives, he shifts it back to the nearest code word in Alice's code before decoding the message. Okay, so the whole process looks like this. You have a collection of messages. A particular message A is chosen. There's an encoding process through using error correcting codes. Then there's a transmitter that takes that, runs it through a channel, comes to a receiver. The result of the receiver goes through the decoding process, and you get a decoding message. And A prime hopefully is the same as A, little a. Okay. Alice's codes use bits, and we almost always will be using about bits. But you could use decimal digits, letters of the alphabet, etc. The number of symbols used in the code word N is important. For Alice's repeat 3 times, the binary code N is equal to 3. The third fact is K, and these are the equivalent number of symbols being represented by the code word. So if Alice's code word, the code word represents 0 or 1, then K is 1. So errors, the Hamming is a 3-1 code in this case for the code that Alice is using. Okay, so they're usually coding theorists are designed, at least for Hamming codes, by N and K. And as I said, using Alice, we get a 3-1 code with a minimum distance equal to 3. That tells us a lot because it tells us a lot about the error correcting properties of the code. So if D were not 3 but were equal to 1, then that would mean the 2 code words were only a single symbol. A single error would turn one code word into another, grove to grave, and that's a potentially dangerous sort of error. If Alice sends, "I will see you in the grove," and Bob receives, "I'll see you in the grave," he might get the wrong idea. So suppose D equals 2. We'll illustrate with our 2-bit code that lives on a square. It's a 2-1 code. The only 2 code words are 0, 0, and 1, 0. If Alice sends a 0, 0, and 1 bit picks up an error, Bob might receive a 0, 1. But it's equally close to 0, 0, and 1, 1, 1. So he wouldn't know how to correct it, and he would have to simply say, "Transmission garbled, please send it again." So he has at least learned that something, if a 0, 1 or a 1, 0 came in, he knows there's been an error, but he doesn't know what it was, so he has to ask the whole set of symbols to be resent.
How does Bob know an error has occurred?
Well, the only 2 legal code words are 00 and 11. So if he gets a 01 or he gets a 10, he knows that one of those things was an error.
So this is agreed upon in advance, is that correct? The
Oh,
only
yeah.
legal code words.
Yeah, that's the way you design the codes.
Okay.
So that's the whole purpose of designing codes, is to have the appropriate signals being sent, and the transmitter, you code it before you send it, when at the other end you have to decode it. So both sides needs to understand all about the codes and how to code and how to decode.
So if a 00 was sent and a 11 was received, both of those are agreed upon. And is that the
That would be
example of your?
That would be a 2-bit error, and he would not be able to figure out that that was an error. He can only find a 1-bit error.
Okay. I had one other question about that box that you showed, cube that you showed, and yeah, no, the previous.
I know, I'm going up. Yep.
Yeah, that one. The transmission can either go 1 length, 2 lengths, or 3 lengths, and those are called distances. And what does a distance translate to? What's the significance? Is it time? Is it distance? Longer distance is fraught with potentially more noise and therefore more error. What is this? The time portion would be taking longer to arrive at the destination.
Well, that's always true. Anytime you use error correcting codes, you use more bits than you did just using the direct, 2 to the n needed to symbolize whatever it is you're sending. However, the distance tells you how likely an error could occur. So if you start with 000, then a distance 1 gives you 1-bit error. So you would have a 001, you could have a 010, and a 100. Those are the 3 possible distance 1 codes. So that any one of those would have a 1-bit error, and that tells you the number of bits that you can properly diagnose and correct. Now, if there's 2-bit errors, then you know that there's been, well, you won't know, you know that there's been an error, but most of the time, the 2-bit errors would be 1 bit away from the 111, which is 3 away. So for instance, the 101 is only 1 away from 111, and the 110 is 1 away from the 111, and the 011 is also 1 distance away. So if you had 2-bit errors, the assumption always is that if there's only 1 possible bit error. You can diagnose in all cases that there is an error, but the assumption in this is because the code can only correct 1-bit errors, the distance of length 1 from 111 is all the codes that were 1-bit errors from 111. and all of the ones at 1 bit away, the 0, 1, 0, the 0, 0, 1, and the 1, 0, 0, those are all the other assumptions that they're all assumed to be bits of 1 error from 0, 0, 0. So that's the way the design of the code is done. Anything of length 1 is assumed from either end, 0, 0, 0 or 1, 1, 1, is assumed to be a 1-bit error. And so if there are 2-bit errors, you'll wind up decoding it as the opposite symbol. So this only works for 1-bit errors. Okay, we've already talked about the NK. We got that. All right, so a D equals 3 allows any single error, a single bit error to be corrected. What about D equals 4? It's really hard to show a 4-dimensional cube, but correcting a single bit error in the code words, that would only be a Hamming distance of 1, and so there's no ambiguity about the original code word. It is the closest one. And the same thing is true for the 1, 1, 1. Either the 0, 0, 0, 0, 0, 0, or the 1, 1, 1, 1. Any 1-bit error would still allow you to correct it. But if there were 2 errors, the middle distance between 2 code words, those would not, you could not detect, because the distance from each of them would be distance 2. You can't detect, you can't correct 2-bit errors in a 4-bit code. But we can, if we get a distance 2 from the code, we know that we've had 2 bits of error. So the distance tells us that there has been an error, but because the distance would be 4 between the 0, 0, 0, 0 and the 1, 1, 1, 1. But it still only corrects the same 1-bit error. It tells you, though, that we're able to detect a 2-bit error, and that's not everything you would like to have, but it's something. So we could look a little further. Suppose we had a 5th dimensional cube. So if we had 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1 as the errors, as the codes, then we'd be able to certainly tell that the distance 2 is closer to either of the others, because the distance between those 2 is 5. So in this case, you'd be able to correct 2 bits of error, and you'd be able to diagnose that a 3-bit error could occur. So D equals 4 corrects 1 error, detects 2. D equals 5 means we can correct 2 errors and know that we've had 2 errors of error. and you can keep, you know, going 6 and etc. as you go up. So if D is an even number, we can detect D over 2 errors. We can correct one fewer than that, D over 2. And if D is equal to 8, that means we could detect 4 errors and correct up to 3 of them. If D is an odd number, then we can correct D minus 1 over 2. And so if it's equal to 13, if the distance was 13, how many errors could be corrected? Shout it out.
6.
Good. Okay. Whoops. All right. So you have a little table here with these things here, and if it's odd, if it's 1, you get no error bits detected, none corrected. If it's even, you have 2, you get 1 detected bit and no corrected bits. 3, you get 1 detected bit and 1 corrected bit. If you have 4, you get 2 detected bits and 2 corrected bits. 5, you've got 2 and 2. Even for 6, you get 3 and 3, and odd, you get 3 and 3. So this is the way the simplest Hamming code works, and how many bits you can correct in any code. So who was Steve?
This goes kind of back to Lee's question. If you had a channel that was really bad, that you couldn't even get, you know, you had 50% error possibility, the error correction concept doesn't seem, because you could send out, you want to send out 5 zeros, and actually what the receiver gets is 4 1s and a 0. The correction would go the, you know, that still shows the possibility of error being in your message transmission.
Right, but if you go to, you know, 13, then you can correct 6 errors and detect 6 errors. So, you know, depending upon how bad the error probability is, there's got to be some length which will allow you to correct all the number of possible errors that are likely in your channel.
I have to think about it. So that the implication is, even with very high error, if you took enough
length symbols, yeah, if you use,
you would okay, all right, I guess that makes sense.
Yeah.
That makes
Bob,
sense.
I think your
Thank you.
entry number 6, your row should be 3 and 2, not 3 and 3.
6.
If you have,
No, it's D over 2 in both cases, the detected bits and the corrected bits.
so 6 and 7 are the same.
Yeah,
Okay.
yeah.
Let me.
Yeah, the only
I'm
one
missing-
that is odd is the 2-bit one, which doesn't allow any corrected bits.
Well, if you have
No,
6,
I'm sorry, there's got to be a problem here. You're right. This is 0, this is 1, this is 2. You're right. These are D over 2 minus 1 up here. So I'll correct this table. My apologies. Thank you for catching that. I appreciate it. Okay, let's take a long look at the famous error correcting code Hamming 7.4 binary code. Hamming was well acquainted with the ideas of information theory because he shared an office with Shannon. And as I said once before, the code, this particular code was used as an example in Shannon's original paper. So what kind of a code is a 7.4 code? Well, N is the number of bits that are sent, 7. And 4 is the number of bits that the code can represent. So 4 bits of information. So 2 to the 4 is 16. So there's 16 possible codes from 0000 to 0001, 0010, etc., all the way up to 1111. So if you do the base 2 representation of 0 through 15, you get the 16 code words. 0 to 15 is 16 length. Okay. So, so we can correct any 1-bit error in this code. And we would have to draw a picture of a 7-dimensional cube, which is pretty hard to understand. But we can say, all right, suppose we have the 4 data bits, D1, D2, D3, D4. These carry the message. In addition, we have 3 parity bits, P1, I'm sorry, those should be subs, P1, B2, and P3. And they're calculated using the XOR function. If you remember from our logic, I'm going to do another YAD2M, yet another diversion to mathematics. So, finite fields. A finite field is a finite set which is a field. And things like, well, the real numbers are a field. The rational numbers are a field. So this means that addition, subtraction, division, excluding division by 0 are defined and satisfy the rules of arithmetic. Those are the definitions known as the field axioms. And a number of elements of the finite field is called its order, or sometimes its size. So a finite field of order Q exists if and only if the order Q is a prime power. So P is a prime number and K is a positive integer, 1 from whatever you want to choose. So in a field, the order of P to the K, adding P copies of any element always results in 0. So the characteristic of the field is P. Prime numbers are the ones that we're used to, 2, 3, 5, 7, 11, 12, ... The rest of all these here. So if Q equals P to the K, all fields of order Q are isomorphic. However you do the computations, they can all be mapped 1-to-1 and onto between those. So, whoops, in a finite field of order q, the polynomial x to the q minus x has the roots of that equation equals 0. There's a typo there, I'll correct that. The roots form a group and a multiplicative group, and so it's a cyclic group. You can just keep, you can always find elements that if you keep multiplying them, they'll eventually exhaust all of the elements of the field. So in mathematics, modular arithmetic is a system for arithmetic for integers. The numbers wrap around when reaching the value called the modulus. The modern approach to modular arithmetic was developed by Carl Friedrich Gauss in 1801, so it's been around a long time. And you're actually quite useful, you're quite used to it because modular arithmetic is clock time. So if you have a 12-hour clock, then if it's 7 and you add 8 hours to it, it will be 3. So that is, simple addition would say 7 plus 8 equals 15, but the clock wraps around every 12 hours. And so you have to take, when it goes over 12, you subtract 12. So 15 minus 12 is 3. So that's how you get the 3. And the hour numbers always repeat after 12. So if you start at 9, you go around, you get back to 9. If you start at 6 and you start around, you get to 6 after 12 hours. So 15 is congruent to 3 modulo 12 is the language that is used in this. But what we're talking about is simply the fact that the numbers repeat always with a fixed number. So there is a couple of truth tables here. So you can take a look at the AND, logical AND, truth table. So true and true is truth. True and false is false. False and true is false. And false is false. That's the usual table. You can do the same thing using modulo 2 multiplication. We put a little 2 on the multiplication symbol, and it's the bit AND. So A bit AND or times sub 2 of B is the same table. So 1 and 1, 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, and 0 times 0 is 0. So they're isomorphic. They're the same, the bits are equivalent to the truth table. There's another type of truth table, which is the logical XOR, and the XOR true is false. True XOR false is true. False XOR true is true. And false XOR false is false. You can use modulo 2 addition, and that gives you an equivalent bit table where 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. And if you think about it, 1 plus 1 goes to 2 in usual arithmetic, but because we're doing it modulo 2, it goes back to 0. That's what, every time you get to 2, you change it to 0. So 1 plus 1 is 0. Is this all clear? Is this straightforward? Anybody have any?
Yes.
Okay. Everything's fine. All right.
Okay.
I think that table is incorrect though, right? An error?
No, what?
1 times 1, you have it as 0?
No, I have 1 times 1 is 1. 1 times 0 is 0. 0 times 1 is 0. And 0 times 0 is 0. You take
Are you
the,
looking at the bit table?
yeah. So if you take this times this, you get this. You get this times this, you get this.
I think
I
she's
see,
talking
okay,
about the other table.
It's
It's the
configured
same
differently.
structure as this.
I see.
True
One
and
on the-
true is true.
The one on
True.
the right.
The one on the right is modulo 2. So 1 plus 1 is 2. Modulo 2 makes it a 0. 1 plus 0 is a 1. 0 plus 1 is a 1. 0 plus 0 is a 0.
Is that the table you had trouble with, Lee Gale?
Pardon me?
Which table did you have?
No,
trouble with?
I was doing it differently than he was doing it. Now that he explained how the method, I understand it.
Okay.
Okay, yeah. So it's identical to the truth table. You got true and true is true.
Yes.
True and false is false. So,
Yes.
okay. So these are isomorphisms. You can use modulo 2 arithmetic and you're getting the logical results. Okay, so the simplest one that we've been talking about here, modulo 2, is z sub 2. That is all of the integers from 0 to infinity are mapped into the even numbers. So 0, 1, all the odd numbers go into 0 and all the even numbers go into 1. And that's using the modular arithmetic that we talked about. And that finite field also can be used as a linear vector space, just as the field R for the real numbers can give you a linear vector space. So we'll start with the Hamming code 7.4, first as a picture, then show the equations, and lastly show some results in matrices for the inner products using the modular arithmetic as opposed to the usual arithmetic. So in a real linear vector space, vectors are columns of real numbers, R. That R represents the real numbers. And the inner products use addition and multiplication. So the linear vector space over Z2 are columns of bits, that is 0 or 1s. And the inner product uses the modulo 2 and the times 2. So let's remind ourselves of how we've got 3 parity bits, P1, P2, P3, and we have 4 bits, D1, D2, D3, D4. So remember, 0 plus 0 and 1 plus 1 are both 0. 0 plus 1 and 1 plus 0 are both 1. So there is a pattern here, and we'll get to it in a little bit, but let's start to try and see a picture. We can use, we have a code word here, 1010. So D1 is 1, D2 is 0, D3 is 1, D4 is 0. We have 3 parity bits, which you can take D1 plus D2 plus D4, D4 plus D3 plus D4, D3 plus D1 plus D4. So if you have D4, it's a 0. If you have D1, it's a 1. If you have D2, it's a 0. D3 is a 1. So if you add these up this way, P1 gives you a 0, P3 gives you a 1, and P2 gives a 1. So you can have 3 parity bits and the 4 code words, and those give you ways to explain how to correct your code being set. These are only good for 1-bit errors. In the original thing that Hamming, the reason he designed this code was because he, like me, used paper tape for his computer computations. And every time that there was a error in the computation, the code that was sent on the paper tape, the computer would understand that there was an error, and it would send an error message and stop the computation. But he said, this is crazy. If it can know that there's an error, it should be able to correct it. So he worked very hard, and using linear algebra, he was able to show how to correct this. Now, we're going to use a different set of symbol numbers here. This was simply an idea to show you how you can do it pictorially, but it's much easier to deal with it in actual mathematics. And we'll take a look at what the picture looks like. You got 3 overlapping circles and a label for each of the 7 regions. Each one of those 7 regions has one of the bits, and the data bits come from the message. So there's, as I said, this is only one of the 16 possible, there's only, the code 1010 is one of the 16 possible ones in here. So the rules for the parity bits are to use the modulo plus operator, the +2, of the 3 bits it shares in a circle with it. So P1, it has D1, D2, and D4. P2 has D2, D4, D3. and P3 has D1, D4, and D3. So the way in which you deal this is you look at all the code words that are around the section where the parity bits are, and you add those in modulo arithmetic. Okay, so the parity bits are set so that each circle contains an even numbers of ones. So if the data bits are 1, 0, 1, 0, the parity bits are 1, 1, 0. Now, you can use this and you can correct it, but it's hard to do it with pictures. So I'm going to switch to equations. All right, so we'll do some simple algebra. And I have to apologize. These should have subscript 2s on all the pluses. That's a typo. Okay, so I'll use a vector of all 7 bits as C1 to C7. And we're going to embed the parity bits in a weird order. The P1 will be C1, P2 will be C2, and P3 will be C4. If you take a look at what the equations were in the previous picture, then C1 plus C3 plus C5 plus C7 equals 0. And C2 plus C3 plus C6 plus C7 equals 0. And C4 plus C5 plus C6 plus C7. All of these are modulo 2 equals 0. So you can solve these 3 equations for C1, C2, and C3. And the remaining C3, C5, C6, C7 are independent. So I can choose the 4 bits in those code words, C3, C5, C6, C7, and choose 4 bits to be the binary integer digits of 0 through 15. So the C3, 5, 7, 6, and 7 could be a 0, 0, 0, could be a 0, 0, 1, a 0, 0, 1, 0, a 0, 0, 1, 1, a 0, 1, 0, 0, etc., until we get to all ones. So these are the binary representations of 0 through 15. You can see that, let's see, this would be 4. So 1 times 2 to the 0 is 1, plus, no, that must be this one. All right. So this is 1. This is 2. This is 3. Oh, I was counting wrong. I thought it was 4 and I was confused. Okay. So 1 plus 2 is 3. So it works. All right. So these are all the binary representations of the possible codes that could be sent down the channel. So if you solve the parity bits using the equations, each do it over and over again, choose one of the codes and put the code in those three equations, the code. So if you choose 0, 0, 0, 0, put it in here, you're going to, everything but the C1, C2, C4 is going to be 0. So those will all go away. That means that the result, the three parity bits, C1, C2, C4, will be 0, 0, 0. If you take a look at this one, C1 will be, C3 and C5 are 0. So C1 will be a 1. Remember, this is modulo 2, so there's no negative results, only positive ones. So C2 will also give you, these two are 0, so this will give you also a 1. And C4 will, C5, C6 are 0, C7. So this will give you 3 bits of 1. So if we go back here, I wonder if I have these in this order. No? All right. So 0, 0, 0, everything's 0. The next one, you get a 1, 1. Then remember, you're using C4. So you get a 1 over here and 0, 0, 0, 1. So yeah, you get a 1, 1, 1. I did the correction. I did the calculation in my head. Wow, that's amazing. I never do arithmetic in my head. Anyway, these are what all the codes are. And C4 is a bit code. This is a parity code, I should say. This is a parity code, and this is a parity code. This, and this, and this are all the code words. And there's 16 of these from 0 through all ones. Okay. So how do we use this? So we've got a received code. So we sent one of those codes. Then we use the parity equations that we had before. And we have x1 plus x3 plus x4, 5 plus x6 gives z1. x2 plus x3 plus x6 plus x7. Again, these are all modulo 2, gives you z2. And x4 plus x5 plus x6 plus x7 gives you z4. So if z is, and these are all modulo 2, I will put the little 2s on after we're done. So if you get a 0, 0, 0 for the parity numbers here, that means no error has occurred. If you get a non-zero result, that is one of those numbers or 2 of those numbers or 3 of those numbers come out to be 1s, then we can compute which bit was in error by using z1 plus 2z2 plus 4z4. And this is in regular. So these are modulo, whoops, sorry. So these are either 0s or 1s, but this tells you which bit number has had an error. So that has to be done in regular arithmetic, regular integer arithmetic. Let's do an example. Oh, damn. I need to correct that, but okay. So let's say we took a look at this particular 10111101. So this was the received code. The sent code would have been 1001101. So the original code was sending a 0101, and the first bit error was incorrectly computed, so you get 1101. And the parity bits are still in there, 101. Not 123, but 124. Okay. So we stick this code, the received code, into our previous equation, and we get 0, 0, 1. Z1 is 0, Z2 is 0, but Z4 has a 1 in it. Then we had our arithmetic equation that uses real arithmetic, not modulo arithmetic. And we get Z1 plus 2Z2 plus 4Z4. So 0 plus 2 plus 4 gives you 4. So 4, remember, is the first bit of a code error, of a code word. So, or is it, no, I'm sorry. So it was a bit error. Sorry, it was a parity bit error. My mistake. So if you turn the 1, 2, 3, 4, yeah, it was a parity bit error. Sorry.
No, wasn't it the first bit of the message? 4 would be the first bit on the message.
Yeah, yeah, right. Okay. Yes. Is that right?
No, that's not right.
That's not right.
No.
Okay. So we have C1 through 7, C2 and 4 are the parity bits. So C3, 5, and 7 are the yeah, C3, C5, C6, and C7 are the code words. All right. So I think I screwed this up in here, but because I'm showing it to be C4, which would be a parity bit error, and it's actually an error in the code. So there's something screwed up in the calculation I did. I apologize. I'll correct it when we close and show the proper results here. Okay. So you should get the proper code result. I somehow screwed it up.
No, but this is still pretty neat. I can see how confusing it is, but this is neat to see.
Yeah. And then furthermore, now we've been doing it all using modulo 2 equations. You can do this all in matrices, again, using the modulo 2 addition and multiplication. But if you have a matrix G, now this is 7 down the column and 4 across. So if you have a 4-bit code and you take G and inner product it with the 4-bit vector, and it'll tell you what the 7-bit code with all the parity checks in this matrix. And in particular, you can see that the third one, the fourth, the fifth one, sixth one, and seventh one all are entries of the identity. So it will reproduce the code that you put in the C3, C5, 6, and 7 positions. And the parity bits these are just the equations that we had earlier for the parity bits for C1, C2, and C4. So you can do this all just, you know, do the inner product, but make sure you do your inner product in Z2, not in R, and that will give you the code to send out. And if you want to determine the parity check H, that allows you to give you, suppose you get a code that we had with one error in it. So that will be a 7-length column, and the rows are 3. So the Z1, Z2, and Z4 are given via the H matrix. So if you have a code coming in, a receiving code, so G shows you choose one of your codes, inner product it with this matrix G, it will give you the sending code. If you've got the receiving code and you inner product it with H, then you will get the 3 Z1, Z2, Z4 parity ones, which you can then inner product with 1, 2, and 4 to figure out which one of the bits was in error. So you can do it all using matrices as long as you use your inner product being plus sub 2 and times sub 2 instead of the usual plus and times. Okay, so that's, I think, pretty much what I wanted to get worked on. Did all of that make sense? Any questions about the?
Yes. What happens with 2 errors?
Yeah, you screwed.
Yeah. Okay. Okay. I like that. It's you just get garbage out of the. It tells you something, and you don't know that. Well, I've always wondered how the parity system worked. I mean, people talk about parity bits, and I've never. So this was well done. This was pretty interesting.
Yeah,
Great.
I agree.
Okay. Anyway, so we now have talked about code systems and error correction codes, and in particular, we described Hamming codes, and we did the famous, I'm sorry, that's a 7-4 code. And next week, I'll do some simple cryptography codes based on using the RSA approach, which uses factoring of 2 large prime numbers in cryptography. So I have a medical appointment that I have to go to, so I have to leave. So I'm going to stop the, where are we? Okay, stop recording.